Today's webinar is entitled Assessing Future Climate Risks and Adaptation Options for Australian Water Systems, and our presenter today is Michelle Ho from the CSIRO. Michelle is a research scientist in the Hydrological Predictions Under Change team within the CSIRO Water Program. She's a contributor to the Earth Systems and Climate Change Hub Project 5.4 entitled Water Futures Under Climate Change. And Michelle has spent over a decade exploring ways to better inform water planning using paleoclimate information, statistical methods for representing key characteristics of climate variability, modelling water systems, and understanding drivers of water resource risks and vulnerability. So just before I hand over to Michelle, I just note that there is a chat function in your Zoom bar, and we'd invite you to put any questions you have throughout the webinar in this chat bar, and at the end we'll endeavour to address as many questions as we can. So please do remember to pop your questions in that chat box and we'll get to them at the end. So without any more ado, I'll pass over to Michelle. Thanks, Michelle.
Thanks, Sonia. Thank you everyone for your interest and for joining us on this webinar from around the country today. I'm going to actually start by acknowledging the traditional owners of the land that I'm currently sitting on, and that's the Ngunnawal people. And they have lived in this region for at least the past 20,000 years and continue to contribute to the life and culture of this city and region. And from my perspective, their understanding of natural resources and ability to adapt to changes in our environment is really an inspiration for much of the challenges we're seeking to address at CSIRO and in this program. So the specific work I'll be talking about today has been made possible by the National Environmental Science Programs project called Water Futures Under Climate Change. But I need to actually state at the outset that I won't be providing you with any information on how climate change will change water availability in your region into the future today. What I will be talking about is an approach we're using to provide context for climate change information and to help assess adaptation options under climate change. So I'll be beginning today's talk with what is meant by climate risks, our understanding of future climate, how these are relevant for Australian water systems, and also what is meant, importantly, by a robust assessment and the robust assessment we're trying to use in our team at CSIRO. So when people talk about climate risks, often they are referring to extreme events such as bushfires, storms, or extreme temperatures at either end of the scale, things that we've witnessed in the past and things we expect to experience again in the future, possibly under different frequencies. But the important part about this risk is that it's actually made up of two components. So one part of risk is the event and how likely it is to occur, so probability of occurrence. And the other part of risk is what impact the event will actually have. And this can be thought of in terms of exposure to an event or the damage that would occur as a result. So in this example here, we have a high risk example on the left and a low risk example on the right, where the risk profile has changed simply as a result of the exposure. Nothing to do with actual nature or climate, but just in terms of what we have placed in the pathway. So these risk profiles become much trickier to estimate once we talk about future climate risks that consider climate change. So climate change projections have afforded us a wealth of knowledge on how our global climate system will largely respond to changes in greenhouse gas emissions. And at the moment, we as a science community have a really high confidence in how temperatures will change across the globe in response to various emission scenarios. But we also need to keep in mind that all of our climate projections are based on equally plausible emission scenarios, which is why you see a number of different global temperature projections on the right. So when we're talking about what we're talking about when we're estimating rare event probabilities, so if we then look at this figure here on the left, is we are talking about something that is projected, and we're also trying to estimate these tail end probabilities. Just for the record, I believe at the moment we are tracking on one of the high emission scenarios, so it's more plausible that we're going down that path. But in terms of, so in this example, we've got temperature on the left, but in terms of estimating other event probabilities, such as rainfalls, storms, or droughts, these exist under a scenario that doesn't actually have an associated probability of occurrence. So now what we're talking about is we're regarding future climate change and looking at the climate impacts rather than climate risks. When we consider water resources in Australia, we're often concerned about not just how much water is available, but also when and where it is available. And traditionally, inadequacies in water supply, which is something we've dealt with since, humans started congregating around dense areas, is something we've addressed through building multi-year water storages and conveyance systems, so that way we can store water into the time periods where we actually need to use them, or we can transport that water into places where we need them. There are currently options for reoperating many of these systems in response to changed conditions, including things like climate change. Water for the environment is a slightly different problem because it's often a question of whether large pulses of water are available for flushing systems or ensuring connectivity, or making sure that water actually reaches the floodplain ecosystems to maintain ecosystem functions. There's also a large step between understanding global climate changes and understanding how this will affect water availability at a specific location, because large-scale climate is filtered through many events and processes, like where storm tracks occur, snowpack dynamics, or how catchments respond to climate, and also how we manage how we manage catchments and the feedbacks that go along with that too. So for example, if we were to clear a certain portion of land, that would change the feedbacks of the water that gets cycled back into the atmosphere, and that will change the overall hydrological cycle. So those sorts of decisions will impact on that hydrological cycle, and that will change the way that we see water in the surrounding environment. So while climate change projections are a really valuable source of information and one that we really need in our toolkit, using this particular tool to drive assessments of water resource risks may be a case of not using the tool in the best way for the job at hand. So in this case, we're talking about looking at climate impacts on water resources. The way climate change projection information has typically been used has been to try to find ways to make it more relevant to whatever problem is at hand. So even though the original goal of climate projections was to inform mitigation of global greenhouse gas emissions, a lot of work has actually been done to try to get climate projections to fit the purpose of informing water management. So at the moment, as it stands, the IPCC has recommended 4 global greenhouse gas emission scenarios to be used as scenarios that we test and as experiments within the suite of recognised global climate models, or GCMs, of which there are currently around 42 in the CMIP5 suite of models. So what will happen is you take those 4 GCMs, run them through all the climate models, which is quite computationally expensive. And ideally you'd run this hundreds or thousands of times so that you can account for the uncertainty within each model. What typically happens in a top-down climate impact assessment is that information then gets fed into some sort of regional downscaling model. And the point of doing this is many of the GCMs are at a very large spatial scale, and we want local information, or at least information that's relevant to our region. So that is fed into the regional climate model, and that's used to then generate runoff time series and estimate the parameters. And then the intent is that those parameters are used to design or implement adaptations. The problem with this approach is there already is uncertainty, which climate scientists are very aware of within each GCM and between each GCM. And when you use that uncertainty in this sort of setup, those uncertainties are cascaded and possibly magnified through this process. The other part is because this process is quite computationally expensive, what normally happens is that people will select certain scenarios to focus on, or that in addition to that, they will also select GCMs that they think are most suitable for the region of interest. They will also use a small number, usually one, ensemble members. So instead of hundreds and thousands of those GCM runs, one or two will be selected just because of computational limitations. And as part of this, you're sort of already narrowing down your the broad information that is available through these GCM experiments. So I think once you start selecting those scenarios and selecting GCMs, you're narrowing the scope of what you think the future projections might possibly be, and they may be opening you up to vulnerabilities in the future. So these top-down approaches are really still needed. I can't emphasize this more. They really are needed for the purposes of brainstorming or shaping adaptation strategies. So they're there for the purpose of planning and thinking about what solutions you put in place if any of these future climates were to eventuate. An alternative approach is to use what is known as a bottom-up approach. So instead of looking at climate impacts through a GCM lens, we are instead starting in the vulnerability space. So with this approach, you start by defining the system that you're interested in, and also identifying the options that you would put in place as informed by that top-down approach. The second step is where you actually test whether the system is actually sensitive to climate, and also to exactly to which climate variables the system operations are critical. So some of the questions that will be answered here are we concerned about peak annual flows or the duration of dry spells, or are we concerned about evaporation rates? So you're starting with what the system vulnerabilities are. That's then used to stress test the system and assess plausibilities of failure. And it's at this point that you can include extra climate information, including those from things like GCMs or downscaled projections. But you can also include other climate information like paleoclimate information, or look at subsets of the historical climate to see where how your system would respond. This sort of analysis then gets fed back into this process to inform whether you've actually, so that you can reassess whether you've actually designed the model in an adequate way, or perhaps the end user would redefine what the objectives are. So another way of looking at this bottom-up approach is through a process of evaluation called decision scaling. And decision scaling sits under an umbrella of robust assessment frameworks. And this wide umbrella of robust assessment frameworks are designed as a way to provide system-specific context for climate information. And it's been implemented by scientists around the world for projects addressing a wide array of water problems, like operating rules for the Great Lakes, looking at combined climate and demand sensitivities for Melbourne water, also even looking at competing objectives, so looking at flood damage versus ecological functions. So as with all bottom-up or robust approaches, the assessment starts by first defining the system performance criteria so that we have a quantifiable measure of the climate impact. And this needs to be defined with inputs from the managers or decision makers of that system. The next step is to build a system model that is fit for purpose. If the goal is to understand how climate change will impact on the system, then it is critical that the model captures the relationship between climate and the inputs that affect that system, whether this is inflow, changes in demand, or other responses. And it also needs to be in a time step that achieves a balance between computational feasibility and capturing an adequate degree of interactions in the system. So that leads us to the third part, where the computational feasibility comes into play, because this is where we need to perform a vulnerability analysis or a climate stress test of the system. And it's in this step where we make defined adjustments to the climate over a sensible range to test the operational limits of the system in response to climate. And this is done independent of climate change projections. So having that model that is of an adequate degree of complexity that captures those climate feedbacks, as well as being able to run through all these stress tests, is really critical, because many systems have models that are very in detailed, often for an urban water resource system. The system model is run at an hourly or sub-hourly timescale, and that sort of granularity means that you wouldn't actually be able to perform your climate stress tests over a meaningful period. The fourth step is where the vulnerability analysis comes into play, and it allows for an assessment of the system performance limits. And this is where you can also provide context for any additional climate information. And it's also a chance to assess your adaptations. It's at this point that the decision goes back to the decision maker to evaluate whether there's a preferred adaptation option or whether they need to reassess the options or criteria for acceptable performance. So that's the overall framework that we're attempting to use, and I'm going to run through a really, really simple conceptual reservoir system just to demonstrate how this decision scaling works before I show you how we've been attempting to apply this to environmental assets in the Murray-Darling Basin. So in this example, we have put in a toy reservoir, so it's one that doesn't actually exist, but we've looked at its performance within a climate system located in Victoria, and we've defined 3 main performance metrics of drought frequency, which is where reservoir levels would drop below this drought level into this red zone. Also drought resilience, which is a measure of how quickly the system rebounds from that drought level and returns to normal operations, and vulnerability as a function of the the demand that is not met. Because it's a conceptual model, I was able to come up with adaptation options that again are conceptual. So we tried 2 adaptation options. One was to curtail the demand, so demand management under drought conditions, and another was to expand the storage under changes in climate. So in this system, we sort of have a climate that looks something like this in the blue line, which shows the mean precipitation around in this region, and the demand that we have imposed contrasts with the supply of water, the natural supply of water, so that we have peak demands around the warmer periods and minimum demands around the winter periods. So as part of that decision scaling process, our second step was to form the system model, which consisted of a climate input, which was generated using a stochastic weather generator model, so that we could look at different sequences and plausible sequences of climate under historical characteristics, climate characteristics. This climate was then fed into the hydrological model, so that was the rainfall runoff model, and in that was imposed, within this model was imposed some storage and release rules, and that they together form the water infrastructure model. This can then be used to calculate the performance metrics, and we ran this 1,000 times under historical variability before performing the stress test. So in the system with a reservoir of 80 gigalitres, which is approximately twice the annual inflow, with that seasonal demand imposed as I showed before, the historic performance resulted in a drought frequency of just under 4% of the months, a drought resilience of 10%. So that means if you are currently in a drought, the probability of you returning to a normal state is just under 10%. And the median vulnerability was 0. So the demand was almost always met. So in the climate stress test example, what we did was we altered that weather generator to force it to have precipitation that was changed from the historical mean. So in this case, we tested up to a 40% decrease in precipitation, And what that resulted in was an increase in drought frequency, so where the level of the reservoir dropped below the drought level. When we forced the weather to have more precipitation, that resulted in decreased drought frequency and more time spent above that drought level. So that was just one of the metrics we used to test the performance of this reservoir. And as I said before, we had 3 of them. So we could also look at how the drought resilience as well as the vulnerability changed in response to shifts in precipitation. So as expected, with decreases in precipitation, your vulnerability increased almost up to the point where none of the water demand was being met, and your drought resilience also decreases. So your chance of coming out of that drought is vastly reduced. Similarly, with more precipitation, your vulnerability decreases, your drought resilience increases. So they were pretty intuitive results, but we can also test this for other climate variables too. So we tested things like precipitation variation, evapotranspiration, we looked at seasonal changes, and we also looked at low frequency changes in precipitation. So that's persistence over multiple years. That didn't have so much of an impact because we're dealing with a system with only a year of memory or so. But the ones that we wanted to pull out were the precipitation and the potential evapotranspiration. And even though they weren't the only climate variables that impacted on this system, we just focused on these 2 because they are variables that are often available from global climate model outputs, which have run climate change experiments. So those projections are often available in outputs. So focused on these 2. And what that provides us with is we're able to look at the full climate vulnerability space as measured in response to potential evapotranspiration and mean monthly precipitation. So the results that you're seeing are again pretty intuitive. This is showing the change in drought frequency. So as you have increased potential evapotranspiration and decreased precipitation, your drought frequency increases up to the point where it is almost always in a drought state. Now, having this climate vulnerability space means that we can also provide context for climate change information. So the little light green dots that you see on that graph are showing you what each GCM, which has been run under a represented concentration pathway emission scenario, which is called 2.6 in this case. It is showing what each of the GCMs say what climate will be like in this region under this emission scenario. So you can see that that spread of model outputs gives you an idea of the intermodal uncertainty, but then you can also look at different scenarios too. So instead of just looking at one scenario and having to pick one GCM or a handful of GCMs, we can look at all those GCMs and see what they say about these 2 climate variables into the future. So this is under RCP 4.5, 6 and 8.5. So with increased greenhouse gas emissions, you're more likely to have more climate models that will tell you that it will be a drier situation for the system. So even though we've provided context for climate change projections, we can also provide a bit of context for what we've seen historically. So if we were just to take a snapshot in time over a certain period of our historical climate, we can say look at the millennium drought, and we can see that that sort of sits somewhere in that dry space too, because if we were to look at all of historic variability, we'd be sitting at this origin and have a drought frequency of under 5%. But under the millennium drought, our drought risk had, our drought frequency had been increased to somewhere about 60%. So at this point, if I were running this sort of decision scaling and I was a stakeholder and I wanted some context around what these GCMs actually say, this is where I'd be consulting a climate scientist to say, all right, can you tell me a bit more about each of these GCMs? Which ones are more plausible for the region I'm interested in? Which ones capture the climate features that actually impact on this region? And then perhaps you can narrow down this broad range that you see here. So another thing that you can look at is an assessment of how those adaptations would operate too. So Under the original system, the median vulnerability, so that is how much of a water shortage you are seeing that you weren't able to supply under these different climates, so changes in precipitation and potential evapotranspiration. And this is showing the volume of water that is not met, the maximum amount of water that is not met under these changes in climate. So this was the original system, just similar to the results that I showed you before. But also, if we were to impose demand management or increase the storage, this is how our vulnerability space would change. So you can see that if you were to curtail demands, then the level of water demands that you are not meeting rapidly drops. And increased storage, while it provides some buffer, you still end up with water shortages at some point, depending on the climate. So again, this is informing what the climate vulnerabilities are, but additional assessments would probably be needed to be made in terms of what the relative costs are of the options, and also to assess who would bear the burden of those costs. Or the decision maker could decide to reevaluate the options with a better understanding of the climate impacts on the system now, and also be provided with that context for climate change information. They may actually decide to revise the criteria of adequate performance. So at this point, that goes back to the decision maker, and this process of decision scaling can either be rerun under the new preferred adaptation options or reevaluated in response to different criteria. But it really is a proactive ongoing process rather than reacting to system failures. So in terms of the Murray-Darling Basin example, we looked at the Lower Murray, and what we were trying to look at were environmental assets and how they would respond to changes in climate. And when we're looking at the Lower Murray, the Murray had been previously modelled into 22 different flood zones. And within each flood zone, there would be unique flooding properties and flood requirements to support various environmental assets and functions. So what you can see here is this quickly becomes a very big problem where you're looking at 22 floodplains, each with 4 different types of environmental assets, with each site having between 2 and 7 site-specific flow indicators. And then also looking at the condition response and recovery path for each of those assets, because these paths are different. For each of those assets, we actually just ended up looking at fish and vegetation, because these assessments were considered a little less contentious compared to birds and aquatic species. So an example of how these metrics work is if a site-specific target flow is met for a year. For example, you'll see that as a grey vertical line. The particular environmental asset will respond to the occurrence of that target flow. So for example, when you have a series of years where that flow isn't met, the condition of the asset deteriorates, whereas for areas where there are several of those target flows that are met, then the environmental asset recovers. So the thing that we wanted to report was the proportion of time spent in a so-called good state, as well as the proportion of time spent in a poor or critical state, and everything in between. We actually didn't get to the stage of defining what those adaptation options were, because when we were working with the Murray-Darling Basin Authority, they had a bit of difficulty identifying management options, given that the inflows into the Lower Murray were largely dependent on state activities over which they had little control. So in this framework, we set up this system model, which ran through and had, again, a weather generator, a rainfall runoff model, aggregating those runoffs into inflows into the river system model. That was a stitched together model of various aspects of the Lower Murray, including the Lower Murray with MSM Big Mod, IQQM to represent the Murrumbidgee, and the Goulburn Broken system model, all in one model. And those outputs were then used to look at site-specific flow indicators and the responses for each ecological asset. So as an example, I'm showing you one flood zone out of the 22. I'm actually only showing one site-specific flow indicator response out of the 7 that were available for this site. So under historic conditions, you can see the, I think 6 different vegetation assets, as well as 2 types of fish, and the proportion of time spent in a so-called good state versus medium, intermediate, poor, critical states. So under historical climate variability, so we tested 100 runs of climate through the system. You can see for this example, something like a river red gum forest will spend approximately 20% of the last 100 years in a good state, and just under 40% of time in a critical or even poor state. So that poor state, I think, is around 20% of the time. But then this is just under historical variability. So we can then do the climate stress test, where we shift that climate. So we looked at things like potential evapotranspiration, mean precipitation, and also changes in consecutive dry and wet days. And those results are pretty intuitive again. Increases in potential evapotranspiration leads to less water and less flows in the river, and that leads to an increased amount of a particular environmental asset spending time in a critical condition. So this identifies the climate variables that are critical to the asset. So there are things that perhaps aren't well represented in global climate models, such as consecutive dry or wet days. So robust assessments, what are they good for? I think one of the primary assets of a robust assessment is that they can provide context for climate change projections, and climate change projections can then be used to guide decisions rather than drive assessments. With robust assessments, the first question that is asked is, what's the goal? You need to first understand what the goals or objectives of your system operation are before you can then think about how climate or other external impacts or external drivers will impact on your system. It also provides a framework for analysis where you can look at your system and look at how far outside the norms things will still work. So at what point will climate actually have an impact? So again, it allows for climate projections to be evaluated in the context of existing and adapted systems. And I've just got a little comic down there showing I guess the thought processes of 2 of my favourite philosophers, in terms of one, that's Calvin, not really having a clear objective and in a sense being incapacitated by indecision because he doesn't know what that objective is. Whereas on the other hand, you have someone like Hobbes, he might have a very simple objective, but because he has identified what that objective is, he has a clear path to achieving it. And that brings me to the end of our talk, and I'd be happy to take questions. I'll hand back to Sonia, and we can work through any questions you have together.
Great, thanks Michelle. Thanks for a really informative presentation. Everyone, just a reminder that if you have any questions for Michelle, we've got plenty of time to address them. So just put them in the chat box at the bottom of the Zoom panel or the top, wherever it is on your screen, and we can get to it. But we do have a question, Michelle, from Joanna, who says, hi Michelle, you mentioned speaking to a climate scientist to reduce the number of model results to reduce the range. In your experience, how feasible is it to remove some of those results, given that the models can have different strengths and weaknesses? Is there a case to be made for retaining the range to highlight the potential range that decision makers might need to consider?
In my opinion, I think there's absolutely a case to be made for retaining all those climate models, because when I've gone and talked to climate scientists, they often will tell me things like, well, each of the models has its strengths. Some of the models may be able to get to model the climate at your region really well, but perhaps they're not actually capturing the whole system, like the whole global features that they are most skillful at doing. I think having all those global climate models in your consideration, in your sphere of awareness, is really important. But there has been a large portion of climate science that has been dedicated to selecting climate models, and I think that would probably be the limit of my expertise in terms of commenting on that. I think we probably have a few climate scientists online who would be better at answering those questions. I think when you're looking at it in terms of a vulnerability assessment, having all those scenarios and keeping all those scenarios and all those global climate model outputs will give you at least a lower bound on the uncertainties that you might see in the future. But another important aspect is not to limit your consideration of vulnerabilities to those global climate models. There's been a lot written in the literature about confining your consideration just to those global climate models, and that can leave you open to surprises and vulnerabilities that were unexpected. So yes, there is a big science in trying to select GCMs, but I think it's primarily been driven by a very practical reason, which is at the moment our computational capacities limit us in how many runs we can explore, and I think that's where the selection of GCMs has come in. But if possible, you would retain all of them.
Okay, thanks, Michelle. On to the next one. It's ecosystem tipping points are often in response to extremes or thresholds, to downscaling GCMs and modifying historical rainfall, runoff and evaporation panels by X% doesn't necessarily represent changes to the climate patterns, climate regimes that generate extremes very well, I feel. How can this be better represented in geological risk assessment?
So I feel like this sort of decision scaling approach goes some way to addressing that, because you can test different climate variables. So most of the results that I see coming out of GCMs are reporting mean values, and you're right, we're sort of more interested in those tail end or extremes because they're the ones that do the damage. I think because you're conducting a stress test of your system, you can have a look at how those extremes will change incrementally and see at what point those actually push your system over. I think in many existing systems, there have probably been historical experiences that have actually pushed that system close to breaking point already. So that gives you a pretty good analogue of, well, at least a pretty good baseline of how your system operates. With a stress test, or with this decision scaling approach, you can also test how your system would respond to those extremes if you have adaptations in place. So that's sort of one of the benefits of that. I think when you go and just scale historic data, even if you don't consider climate change and you're just scaling to a specific part of the historical record, you can already be missing out on what are probable extreme events. So that's an area where statistical hydrology and statistical climate has come into play, where you can actually sample those tail ends without just scaling the historic record, because I think it's been shown over and over again that the historical record is not a complete indicator of events that could occur under natural climate, so not even considering climate change. And having this sort of decision scaling framework allows you to explore those too. Was there anything else in that question that I missed?
I think that probably covers off. I guess
whoever wrote it, if you want to clarify or get in touch later, please do.
Fabulous. Thanks, Michelle. So the next question is from Simon, who says, Michelle, your abstract referred to determining what climate information is most important for the management of water systems. For the example of the lower Murray-Darling Basin you gave, what did you find is the most important information?
So I feel that I wouldn't be able to tell you exactly what climate variable was the most important, because again, we were somewhat constrained by computational capacities. So of the climate variables I tested, things like mean precipitation were obviously important, but variability was also just as important. And that's something that's often not picked up in climate projections, even though it's been hypothesized that that would likely change into the future. Another aspect that we tested was looking at persistence in interannual variability, and that had quite a large impact too, because particularly when you're looking at ecological responses that really depend on sequencing of events, if you were to model your climate so that you miss capturing that characteristic of persistence, you're sort of setting yourself up to miss those responses. So I think with the system, what I saw with a system as complex as the Murray is that there are many aspects of the climate that impact on the system, and it'd be pretty hard to place a value on which one was more important, because when they occur in conjunction, which is something that I was able to look at in the toy model case, what you find there is often the combination of climate impacts is sort of the crux, the one that really stresses your system the most. I guess with the Lower Murray, we sort of just focused in on mean changes because that was sort of the easiest to do. It is a work in progress, and I would like to extend on that. So I'm afraid, Simon, I'm not going to point out and say this one variable and this one characteristic is the thing, because I don't believe my work so far is able to pinpoint one. It would be a suite of them.
Okay, thanks. The next question is from David, who says, for your toy model case, you tested sensitivity to winter rainfall decline versus summer rainfall decline. Which is more important?
So what I was hoping to see there was that a decline in winter rainfall would reduce the amount of storage that you'd have, and that was pretty evident. I thought the interesting part about summer increases in summer rainfall was that it was sort of topping up the reservoir over a period where the demands were highest. They did have a different impact because if you just look at percentage changes rather than absolute changes, there was already a higher winter rainfall in the region. So as a percentage change, that's obviously going to change more. Another thing we looked at, which I didn't show here, was just changes in seasonality. So maintaining the same amount of rainfall through the year and just shifting when it occurred. And that had an impact on the system too. Because if you shift winter rainfall to summer rainfall and maintain the same mean annual rainfall, it's not replenishing the system when the demands are lower. So that did change the risk of the vulnerability profile there too.
Fabulous. All right. The next question is from Neil, who says, great talk, Michelle. Thanks. How well do you think these methods extend to integrated planning across other sectors? For example, agriculture, emergency management, human health?
Human health as well. I think soon after Sonia put up an ad for this webinar, I did get a call from someone in Ag and Food and CSIRO asking about this sort of approach. So this sort of, there have been many examples of this sort of decision scaling approach being used elsewhere. So I think I mentioned things like reservoir or operations of the Great Lakes. A really interesting case where they looked at, another really interesting case where they looked at competing objectives of environmental flooding versus flood damage. So that's, I guess, an environmental application. With agriculture, I've been talking to someone at the Bureau of Meteorology looking at the impact on fruit propagation. So trying to figure out what climate variables will impact on that the most, and also whether we can link that to larger scale mechanisms that the GCMs tend to do much better with in terms of assessing impacts on fruit production. So someone within Ag and Food in CSIRO called about wheat production, and we were just chatting through how we could possibly implement this sort of framework, because I think they'd sort of come to the end of the natural progression of looking at top-down approaches, and we're trying to seek ways to inform wheat production across Australia. So yes, I think there's potential for applications there. In terms of emergency management, I'm guessing things like bushfires, and I think understanding the climate drivers of bushfires is, I know, a whole science in itself right now. But if we were able to form a model that could adequately capture those links, I think that this could help inform the climate impacts. In terms of health, again, it'd be trying to find some way of linking health to climate. So I think the applications are pretty broad. It's just a matter of testing them out, and I guess this decision scaling approach has been around for about a decade, but I haven't seen any applications in health yet. But I'd be interested to hear if you think that could be applicable.
Fabulous.
Or if we could work to actually form a model like that. Sorry, Sonia.
That's all right. So that's the questions that we have at the moment. If you do have any more questions, please quickly pop it in now for Michelle. Otherwise, we might just wrap up. I think we've had some really fantastic questions, so thank you very much. And thank you, Michelle, for a really great presentation. Just a reminder that we do record all of the Hub's science webinars, and so we will have a recording of this webinar on the Hub's website by the end of the week. And also just a quick note about next month's webinar, which will be provided by Helen Phillips from the University of Tasmania on the 22nd of October. And it'll be discussing various ocean currents. So an email will be sent out regarding that webinar closer to the date. So we don't have any more questions coming in, so we might end it there. So thanks again, Michelle, and thank you everyone for attending. Thank you.
Sonia, thanks everyone.